Welcome to the first in a series of webinars to introduce the 5th edition CPCI Design Manual. My name is Ariane Sabourin. I am the Marketing Manager for CPCI. We are delighted that you have taken the time to join us for today's webinar, which highlights the new additions to Chapter 1, Methods and Materials. Today's presenters include Dr. Paul Gauvreau, PhD, University of Toronto, the Editor-in-Chief of the Design Manual, who will provide a general introduction and overview of the new CPCI 5th edition Design Manual. And Robert Burak, President of CPCI and the editor for Chapter 1, who will present some of the changes and additions to the chapter. We would like to first acknowledge the gracious support of our CPCI member sponsors of the Design Manual webinar series. Thank you to BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. It is this type of support from our members that assures CPCI can continue to develop and deliver high-quality programs and services such as this, and to build on our body of knowledge for the architecture, engineering, and construction industry. Today's webinar will start with an overview of Chapter 1 by Robert Burak, and will follow with an overview, scope, and general introduction of the 5th edition Design Manual by Dr. Paul Gauvreau.
Thank you, Ariane, and thank you to everyone who has taken the time out of their busy schedules to join us today. Chapter 1, Materials and Methods, is an introductory chapter that sets the stage for the rest of the more detailed design and other chapters of the Design Manual. For educators, it can provide an important overview and introduction to the unique features of precast and pre-stressed concrete by introducing students to the various products and applications and an overview of the materials used in its manufacture and design. For practicing professionals, the chapter goes into great detail to highlight a multitude of applications for precast and pre-stressed concrete. It provides photographs of previous projects and sample detailed drawings, designed to get practitioners thinking of opportunities for the next project. Chapter 1 is divided into 3 main sections. The first section, 1.1, is by far the largest part of the chapter, at just over 60 pages. It's divided into 10 sections, all of which have been updated with applications ranging from parking garages, residential, commercial, education, institutional, and architectural, to name a few. The second section, 1.2, provides an overview of the general requirements for the raw materials for concrete mix design, the provisions for reinforcement and connections, and the unique requirements of both as they apply to precast concrete applications. The requirements are in the context of the latest CSA standards. The third section, 1.3, is unchanged, and it provides a very general overview of post-tension considerations. For Chapter 1, I'd like to highlight the new short history section, the updated application sections, the newly added detailed drawings from our Structural Solutions Best Practice Guide, and in addition, I'd like to highlight some of the significant changes to the National Standard on Precast Concrete, CSA A23.4, the latest version, which was published in 2016. Moving on with section 1.1.2, this new section is entitled A Short History of the Precast Pre-Stressed Concrete Industry in North America and Canada. Let's have a brief look at some of the milestone projects that are highlighted in this section. The Mosquito Bridge in Vancouver, built in 1952 and shown here, has the distinction of being the very first pre-stressed concrete bridge built in Canada. At the time of its construction, this bridge, when compared to the steel structures of the day, this new technology proved to be both economical and satisfactory from a structural viewpoint. The bridge is still in service today, having been widened on both sides over the years, and was recently acknowledged for its historical significance by the Canadian Society of Civil Engineers. The Royal Canadian Yacht Club footbridge, shown here, is a favorite of Dr. Paul Gauvreau's. It was designed by Lawrence Casale and built in 1958. The bridge spans a narrow inlet off of Toronto's Inner Harbour and is a pre-stressed concrete tied arch structure with span of 48.8 meters and a rise of 6.1 meters. At the time of its construction, it was the longest spanning pre-stressed concrete structure in Canada. This structure is a fine example of how precast and pre-stressed concrete can be used to create structures of great slenderness, and stands as a testament to this design philosophy even today. Another significant project during this period was Grosvenor House, a residential apartment building constructed in 1960 in Winnipeg. This apartment building was originally designed as cast-in-place concrete, and the city of Winnipeg was just accepting pre-stressed concrete at the time of construction when an alternate design was prepared in precast with the assistance from Lawrence Casale. When completed, the 8-story apartment building was the tallest all-precast building in Canada. It too is still in use today. Significant bridge construction projects continued in the 1960s. The Veneer Bridge, shown here, was built over the Columbia River in BC in 1964. It's a spectacular 5-span, 408-meter-long bridge that stands 55 meters above the fast-flowing Columbia River. Precast pre-stressed concrete hexagonal piles support the piers. Precast diaphragm elements were also used in the cast-in-place bridge piers. The Bensford Bridge, shown here, was built in 1969 in Peterborough, Ontario, and was significant at the time for refining splice girder techniques. This eventually led to the construction of many other splice girder bridges across Canada. The bridge was continuously post-tensioned over all 5 spans. 1972 saw the construction of Bear River Bridge in Digby, Nova Scotia. This was the first precast segmental box girder bridge in North America to be built using the short line match casting method. The curved bridge is 609 meters long with 145 single-cell box girder sections. 1975 saw the construction of an innovative clinker storage silo in St. Constant, Quebec. This conical structure used to store 109,000 tons of cement clinker is entirely constructed above ground using precast pre-stressed concrete elements. The circular structure is divided into 64 equal segments, and it's still in full use today after over 40 years of service. This is a photograph of Bromley Place in Calgary, Alberta. It's a 31-story total precast apartment building built in 1977. At the time, it was, and still remains, the tallest totally precast concrete building in Canada. The building was far ahead of its time. Although many total precast residential buildings have been built over the years, most have been mid-rise, and only recently have we begun to see developers building more high-rises of this size and scope in Canada. The Vancouver, BC Advanced Light Rail Transit, or ALRT, was constructed in 1982 to 1986. The aerial guideway is a 16-kilometer long ribbon of precast pre-stressed concrete that follows the curvature of the track profile. This project was the largest precast contract ever awarded and one of the most complex precast projects ever built in Canada at the time. The pre-stressed straight and curved box girders were found to be the most economical solution for the aerial guideway. 1981 to 83 saw the construction of the innovative Calgary, Alberta Saddle Dome, a featured venue when Calgary hosted the 1988 Winter Olympics. The building form is a 67.7 meter radius sphere intersected by a hyperbolic paraboloid generating the roofline and a plane to delineate the base. The entire structure is of precast pre-stressed concrete construction. Also built for the 1988 Olympics was the Olympic Oval. This structure features a unique precast pre-stressed concrete segmental arch roof that resulted in a world-class lattice arch structure built on a very austere budget. And no accounting for the accomplishments in pre-stressed concrete in the 20th century would be complete without including the Confederation Bridge. This is a 2-lane fixed-link 12.9-kilometer bridge spanning from New Brunswick to PEI and constructed from 1993 to 1997. The main bridge has 44 250-meter spans that rise up to a navigation channel in the middle of the structure. This bridge was significant in its use at the time of the latest in high-performance concrete technology. It was the first structure of its kind to be designed to achieve 100-year service life. When One King West opened in 2005, the 51-story structure rising to 176 meters above the street level represented the first significant new hotel in downtown Toronto in over a decade, as well as being the city's first real condo hotel. The tower rises up through and above the Dominion Bank building and is the most slender building in the world and the tallest residential building in Canada. Significantly, there are 1,071 precast panels covering 8,640 square meters installed on the One King West Tower. This is a testament to the scope and potential for architectural precast and for precast concrete building envelopes. Completed in 2012, the Hodder Avenue Underpass is the first structure in North America to incorporate precast UHPC pier cap and pier column shells, along with high-performance precast concrete box girder parapet walls and approach slabs. Field connections, joints, and closure strips were field cast using UHPC, resulting in smaller, simpler joints with superior durability. The project demonstrates that the use of precast ultra-high-performance concrete bridge elements combined with field cast UHPC connections gives designers an opportunity to advance bridge performance, shorten construction time, and extend the durability of these spans. So moving on to an overview of the other sections of the Chapter 1, Section 1.1.3 provides a brief introduction to some of the design philosophies for total precast structures. Shown here on the left is a depiction of a rigid frame system where all the lateral loads are transferred to a moment-resisting frame that ties beams and columns together with rigid connections. In this design, the need for shear walls is eliminated. Although not used very often because of its higher cost, the beam and column framing can be used in combination with shear wall systems. Also shown is the exterior shear wall system. In general, the exterior shear wall system permits greater design flexibility because it eliminates the need for a structural core. By combining gravity load-bearing function with lateral load resistance, the exterior shear wall system is also, in general, considered to be more economical. Finally, the interior shear wall system is depicted. Here, the lateral loads are transmitted by floor diaphragms to a structural core of precast shear walls. Section 1.4 introduces the reader to some of the different types of manufacturing methods. Shown here are curved wooden form. Wood forms are typical for most architectural precast production. Also shown on the right side is a steel form for long line casting of repetitive pre-stressed wall panels. These photos show the fabrication and stripping of pre-stressed concrete piles. Pre-stressed concrete piles are used commonly in Western Canada as dictated by the soil conditions. And this photo shows the fabrication of typical bridge girders. It's always interesting to note when you look at these images, the tight tolerances of the reinforcement cages. These tolerances are much easier to accomplish in a precast facility. It's also interesting to note the amount of reinforcement in a small cross-sectional area, and it speaks to the reason such technologies as self-consolidating concrete have become commonplace in most precast facilities. The next several slides highlight sections 1.1.5 and 1.1.9 of the chapter. These sections provide excerpts from the CPCI Structural Solutions Technical Guide, which can also be found online at cpci.ca. Included are generic detailed drawings to assist designers with their specifications and drawings, all of which were provided by Dr. Medhat Gabriel of HGS Consulting, editor of Chapter 3. Section 1.1.5 highlights the structural elements and the applications for total precast structures. These elements include typically beams, columns, double T's, hollow core planks, inverted T's, spandrels, stairs, and shear walls. Long and short span parking garages are also introduced, and the typical configuration of the elements are shown here. Pages 1-24 to 1-27 include sample parking garage details. Shown here are 3 details: pre-top double T's supported by an inverted T-beam, an L-beam, and a wall corbel. Here's a close-up of the detail for the pre-top double T's on the inverted T-beams. Welded connections join the double T's to the inverted T-beam. A cast-in-place topping is used in a closure strip, and in this case, a slope pre-topping on the double T ensures positive drainage. These next 3 slides show other general details for parking garages. You can see here a pre-top double T, this time with a cast-in-place wash at a wall intersection. Also, double T's supported on interior walls, double T's supported at the top of the wall, and finally a double T supported on a spandrel. Here you can see 3 more spandrel connections, one load-bearing on an L-shaped spandrel, and the other 2 are non-load-bearing conditions. The 4th detail is for an inverted T-beam to column. Finally, these details show an inverted T-beam at wall connection, a double T flange connection, and a spandrel flat column connection. Section 1.1.5 also provides examples of residential, commercial, educational, and institutional applications for total precast structures. Shown here is the Agnes Hodge Elementary School in Brantford, Ontario. Double Wythe insulated wall panels, solid interior wall panels, and hollow core floor and roof slabs were used to construct the school. These projects are great examples of accelerated building construction. For this school, complete installation of all 180 precast components took only 3 weeks to complete. Pre-stressed fully composite wall panels are also introduced in this section. These wall panels can generally span 2 to 3 stories in height. Shown here is a typical commercial application for a theater. This same type of construction is also used for industrial applications. The manual also describes precast concrete residential applications. Related to this discussion, here's a short video that provides a great overview of a mid-rise residential application in Fort McMurray, Alberta.
Developers who use total precast systems confirm that precast construction can shorten a project timetable by 6 to 8 weeks compared to other building systems. This time savings can be critical in bringing a new building into a competitive marketplace or in meeting a tenant's need for occupancy by a specific date. Calgary-based developer Centron Residential Corporation has taken a fresh approach to the design and construction process. Centron recognized that precast concrete would provide many benefits if the project design was tailored to suit a total precast system. To capture the benefits of precast solution, the design team consisting of Centron, Gibbs Gage Architects, TRL Structural Engineers, and Lafarge Precast Division with consultant Cassian Dick and Associates was assembled at the conceptual stage long before any lines were drawn on paper. The entire project was modeled using Precast Concrete PC 3D software. The 3D model was used during the design development by the owner, architect, engineers, and precaster to assist in the design development, make design decisions, and increase the speed of approvals. These residential buildings are total precast concrete structures built using columns, shear wall panels, 10-inch hollow core floor slabs, elevator and stair cores, including stairs, exterior architectural precast insulated sandwich panels, and balcony units. The total precast structures feature an insulated wall system that serves as the building envelope. Windows are pre-installed at the plant. When the panels arrive on site and are installed, the wall system is complete. There is no need to hoard the building to create a temporary heated space. The precast panel system also provides the exterior architectural finish, creating a red brick look balanced with flat accent areas. An innovative framing method created by the design team allows the wall system to be staggered, providing a look that has traditionally been difficult to achieve using precast components. This method also allows the balconies to be cantilevered from the building surface, differentiating these buildings from previous precast solutions. Construction started late August 2006. The first precast building was completely erected in only 62 days. Considering the magnitude and the innovative construction methods, the Eagle Ridge Total Precast Concrete Construction Method could easily set a new standard for multifamily residential construction for years to come.
Pages 1-35 to 1-40 include sample residential, educational, industrial, commercial details shown here. This first page, excerpted from the manual, shows details for both a precast column base and a precast wall base to foundation. These excerpted details show a few beam column connections, a precast beam on a continuous beam precast column, and continuous beam to column connection. More floor connections are shown here. This time, hollow core floor slabs with beams, walls, and columns are added. A variety of details are excerpted here, hollow core and steel lintels, as well as a few wall-to-wall connections. Finally, excerpted here are more wall connections, interior corner and hollow core to exterior walls, load-bearing and non-load-bearing conditions. Section 1.1.5 also introduces the reader to stadiums and arenas. Typical elements include raker beams, stadium risers, tub seating, and vomitory walls. It's interesting to also note that Chapter 7 now includes design tables for single, double, and triple stadium risers. Many types of stadiums, small and large, have been built by CPCI members across Canada. This is an example of a 6,000-seat stadium in Hamilton, Ontario. In this example, precast concrete stadium risers were supported on a steel raker and frame system shown on the right. Pages 1-42 to 1-43 of the manual include sample stadium details. This slide shows the excerpted details for stadiums including raker beam to wall and various stadia seating connection details. Other details include raker beam to column and stair to vomitory wall. Section 1.1.5 finishes off with an introduction to a few other notable applications, such as girders, where a chart of typical girder types and span ranges is included on page 1-56, tunnel liner segments, and precast piles. Section 1.1.6 introduces the reader to precast concrete storage and treatment tanks. In this type of application, the tanks are pre-tensioned vertically and post-tensioned horizontally, and the joints are closed with field-placed concrete. The result is a sealed tank that acts monolithically. Architectural wall panels are introduced in section 1.1.7. Detailed information on the design consideration for architectural wall panels can be found in Chapter 5 of the Design Manual. In addition, readers can also find more information on the design of architectural precast wall assemblies in the recently published CPCI technical publication, Architectural Precast Concrete Walls Best Practice Guide, authored by M.E. Hackborn. Section 1.1.8 provides an introduction to veneer face wall panels and formliners. Both of these systems provide an economical and efficient way to produce a variety of textures and finishes. This is also covered in greater detail in the previously mentioned guide by M.E. Hackborn. Double Wythe insulated wall panels are introduced in section 1.1.9. Besides this design manual and the best practice guide, CPCI also has a number of resources to support the design of these systems. the rain control guide, a maintenance guide, and a guide on meeting and exceeding building code thermal performance requirements, all published by RDH Building Science. Section 1.1.10 introduces the reader to ultra-high performance concrete. UHPC is ideally suited for situations requiring high compressive strength and tensile strengths, long slender elements, long service life, and complex architectural shapes as shown here on the left. The photo on the right is the UHPC inverted T pier cap from the previously mentioned Hodder Bridge in Thunder Bay. More details on UHPC design and the material itself is also included in section 1.2.5 of this chapter. It's also interesting to note that the next version of CSA A23.1, which will be published in 2019, will include a new comprehensive annex on UHPC. Chapter 1, section 1.2.1 references these relevant standards for our industry. CSA A23.1/2 was published in 2014 and is entitled Concrete Materials and Methods of Concrete Construction. Although this standard governs primarily cast-in-place construction, there are a number of concordance items with CSA 23.4, which are highlighted in that standard. CSA 23.4, published in 2016, is entitled Precast Concrete Materials and Construction. It's the governing standard for the precast industry. There are a number of significant updates that I'll cover in separate slides to follow. CSA 23.3, published in 2014, entitled Design of Concrete Structures, governs the design of buildings and most other concrete structures except bridges. Chapter 16 covers the unique requirements for precast concrete. For example, A23.3 allows an increased material resistance factor of 0.7 for precast concrete members that are certified in accordance with A23.4, and that's in recognition of the quality control and accurate placement of forms and reinforcement. CSA A3000 is the cementitious materials compendium and was published in 2013. It contains the testing, inspection, chemical, physical, and uniformity requirements of various cements, blended cements, and supplementary cementing materials such as fly ash, blast furnace slag, and silica fume, all used in the construction and production of precast concrete. CSA S6, published in 2014, is a Canadian Highway Bridge Design Code, and it contains provisions for all types of bridge structures, including special provisions for precast and pre-stressed structures. CSA S413, published in 2014, is a design of parking structures. It covers the design and construction of new parking structures, including durability requirements. In addition to cast-in-place concrete, it also includes provisions for precast and pre-stressed concrete. Finally, CSA S806, published in 2012 and reapproved in 2017, is entitled Design and Construction of Building Components with Fiber-Reinforced Polymers. It governs the design of components using fiber-reinforced polymers and structural precast elements reinforced with FRP. CPCI also provides guide specifications for structural, architectural, and hollow core on our website. Section 1.2.2 reviews the materials for concrete and some of the typical high-performance concretes that are used in the precast industry. Shown at right is a typical self-consolidated concrete mix. As a side note, CPCI expects to produce a best practice guide on self-consolidating concrete later in 2018. A significant and important change to the CSA 23.4 standard is that curing requirements for precast concrete are now standalone and do not reference back to the requirements of CSA A23.1. These revised curing requirements recognize the controlled environment for precast manufacturing and allow for air drying after 1 day curing for both accelerated and non-accelerated cured concretes, with certain provisions. These changes to the curing requirements were informed by research at the National Research Council of Canada and at the University of Toronto. These research reports are on the CPCI website under Technical Publications and are also summarized in the CPCI Technical Guide, Curing of High-Performance Precast Concrete. There are a number of other important updates to the CSA A23.4 standard. They are listed here and also highlighted in the chapter. These final sections highlighted here are specialty sections of the chapter that will also be of interest to the designers. Each section includes further reference sources for the reader. I would now like to turn the discussion over to Dr. Paul Gauvreau, Editor-in-Chief of the 5th Edition Design Manual, who will provide an historical overview and scope of the manual.
Good afternoon, ladies and gentlemen. In 1964, the Canadian Precast Pre-Stressed Concrete Institute, CPCI, published the first design manual in North America on precast pre-stressed concrete. This was a major undertaking at the time and it consisted of 4 parts. Part 1 contained the CSA standard A23.4-16 and a commentary. Part 2 contained design theory and practice. Part 3 dealt extensively with connection design, and Part 4 contained sections on specifications and plant standards. In the 1970s, CPCI undertook what was to become the single largest undertaking in its history, the publishing in 1978 of the first edition of the CPCI Metric Design Manual. The manual was written entirely in SI units with extensive references to Canadian design codes. In 1984, CPCI published a second edition of the CPCI Metric Design Manual. This decision was based upon extensive revisions to CSA standard A23.3. The third edition of the CPCI Design Manual, published in 1996, introduced significant changes in the state-of-the-art for precast pre-stressed concrete, plus important changes in A23.3 that recognized the benefits of quality control in certified precast concrete plants. The fourth edition was published in 2007. Among other important updates, it included changes to element design arising from an increase in the concrete resistance factor in A23.3 from 0.65 to 0.7 for precast concrete produced in a precast plant certified in accordance with A23.4. The CPCI Design Manual is intended for design professionals, professors, students, and precasters. It represents today's state-of-the-art in knowledge and understanding of the design and manufacture of precast and pre-stressed concrete. It is informed by the latest in research and experience both in Canada and, where appropriate, internationally. Substantial effort has been made to ensure that the 5th edition of the CPCI Design Manual is accurate. The design professional must recognize that no manual, design guide, or code can substitute for experience and engineering judgment. This publication is intended for use by professional personnel competent to evaluate the significance and limitations of its contents and able to accept responsibility for the application of the material it contains. Users are encouraged to offer comments to CPCI on the content and suggestions for improvement. Questions regarding the source and derivation of any material in the manual should be directed to CPCI. I would like to acknowledge the people responsible for developing the 1st, 2nd, 3rd, and 4th editions of the CPCI Design Manuals. Readers can refer to these editions for the names of the more than 100 contributors. They laid the foundation for this 5th edition. A wide range of consultants, university professors, and industry professionals gave generously of their time to prepare material and review draft copies and final proofs of this 5th edition design manual. We gratefully acknowledge the contributions of each of the chapter editors and section editors for their thoroughness, dedication, and time to update each of the chapters of the manual to current practice. You can see this on page 3, as well as each of the peer reviewers for each chapter, also shown on page 3. We also gratefully acknowledge the generosity of a number of different entities for permission to use certain materials and tables in this manual. For example, PCI, the Precast Pre-Stressed Concrete Institute, the National Research Council of Canada, and the National Building Code of Canada, the Reinforcing Steel Institute of Canada, and the Research Council on Structural Connections. Most importantly, we would like to acknowledge the CPCI Technical Committee for their continued oversight during the process of the development of this manual and contributing the necessary funding through their annual budget approvals. And finally, Deb Stover from Image Media in Sterling, Virginia, for her excellent attention to layout and design of the manual. Please mark your calendars for the upcoming webinars on the remaining chapters for the design manual. Similar to this webinar, you can register online at cpci.ca. And once again, we would like to thank our sponsors for this webinar series. And now we would like to open the seminar up for questions. You can type your questions in the Q&A text box on your screen. So thank you very much, and I'll hand it back to Robert.
Thanks, Paul. We'll just look at the Q&A questions here. There's a question regarding UHPC. Are there design methods for elements using this concrete considering the varying properties of the UHPC? Paul, I know that on CSA A6 you're doing some work on that?
That's correct, Rob. There is, you mentioned in your part of the presentation that for the A23.1 standard, that there would be an annex related to a material standard for UHPC as a material. And in CSA standard S6, the Canadian Highway Bridge Design Code, in parallel, there's a task force that will be working on a non-mandatory annex with suitable design provisions for structural elements constructed of UHPC. This should be in place for the 2019 edition of the CSA standard S6. I don't think that there's anything underway right now for the A23.3 standard, but you know, I would say a designer could probably take some of the material from the S6 and perhaps incorporate it using suitable engineering judgment into structures other than bridges.
There's another question saying, I'm interested in the sample detailed drawings that you showed. Is it possible to get them by email as separate files? So yes, we can send you PDF versions of those if you're interested, and you can use those to develop your own CAD type of details for your job-specific requirements. Another question here. Some of the historical projects are interesting. I am particularly interested in the lattice arch structure of the Olympic Oval. Is it possible to get more information on that project? And actually, that project is listed as one of our great Canadian projects. When we had our 40th anniversary many years ago. So there's a complete presentation on that project. So if you're interested in that, you can email CPCI at info@cpci.ca, or any on any of those projects. We probably have some more specific details for you on those. So there's a question on CSA 23.4. The curing requirements are different from CSA 23.1. Can you expand on the differences? So essentially, the differences between the two standards, this 23.4 now recognizes the tight quality control and controlled conditions that we have in a precast facility. So what it enables is elements to achieve a certain percent strength, for example, 40 or 70% of your strength, depending on your class of exposure, and enable it to be air cured after stripping at that time, rather than extended curing that's required in A23.1. And all of that was informed by that research at NRC and at the University of Toronto. Specifically for CXL and C1 types of concretes, the research showed that those accelerated cured concretes with the appropriate amount of supplementary cementing materials, actually the SCMs actually mitigated any negative effects that accelerated curing could have on the concrete. So those are the essential differences, and you can look at clause 23 of that standard for some of the details. So the last one here, Paul, looks like it's a good question for you. I'm a professor of civil engineering. Do you have resources to assist with class instruction?
CPCI does have resources. CPCI runs a professor's workshop every 5 years to coincide with the new design manual. So the most recent version of that was in the fall of 2017 to introduce the new 5th edition There's also a wealth of resources available online at the CPCI's website, cpci.ca, under the tab Academic Resources.
Someone's asking about the software that's used when you're analyzing precast slabs. Most designers are using Concise software, and it's available through one of our members on our website. If you look under the associate member website or web listings of our members, Black Mint Software is the company. I used the PCI manual to determine the thermal effect on precast concrete members. I haven't looked yet on the current manual, but is that different than the CSA A23 conditions? I'm not sure what the answer to that one is, and I guess that's going to be covered. I'm trying to remember which chapter that's covered in. Paul, do you remember if it's chapter 5 or 6?
Yeah, it is covered in one of the chapters, and I believe that the requirements basically are similar, pretty much identical to the A23.3 conditions. And so I would say if you're interested in thermal effects on precast concrete members, please register for the subsequent webinars, and that should be covered in further detail at that time. Or, look in the manual. You mentioned in your question that you haven't looked at the current manual. I think it is explained fairly clearly there, so that would be a good first step.
It is chapter 6. I think those are all the questions that I see. And I'd like to thank everybody for their time this afternoon. We appreciate your time. And the next webinar is next week on May 30th, and it's chapter 2 of the design manual. And that will be presented by Wayne Cassian, who's the editor of that chapter. Thank you very much.